The Morera's theorem is in some sense the converse of the Cauchy's theorem. We remember that the Cauchy's theorem tells that an analytic function which is analytic interior to some simply closed contour is always as an integral 0. Morera's theorem is in some sense the opposite. Let us consider a function f which is continuous in a domain D and assume that the function, the integral over c is 0 for all closed contour c in D. Then it turns out that f must be analytic in the domain D. By using this Morera theorem, we are able to state another theorem which is rather fundamental in some sense, and it also comes as a surprise because it's a very strong theorem. If f is analytic in a point, then the derivative of f of all orders also is analytic in that point. Let's turn to the third theorem in this video. Liouville's theorem states the following: if f is an entire function which is bounded, then f must be constant. So it's impossible for a function to be bounded unless it's a constant. And this is completely different from the real case. Consider, for example, this function which has which is infinitely differentiable. It looks like this. It's differentiable for all values on the real line, and it's bounded. It's less than the value 1. The absolute value is less than 1, but it's not constant. So in the complex case, if the function is differentiable in all points and bounded, it has no other, we have no other choice than to conclude that this function must be constant. Also a very useful and strong result. The proof is rather simple in using Cauchy's general integral formula for this special form of it when n is equal to 1. You remember this formula, and it takes this form. If we know, recall that a function which is analytic does not need to be analytic, sorry, but this function must be integrable along any this specific contour CR, which is a circle with center at set 0. Then if this function is bounded at least less than some number, absolute value less than some number m, then we have proved earlier that the absolute value of this integral will be less than the curve length, which is 2 pi r, where r is the radius in the circle, multiplied with the value which the absolute value of g of z is less than. So this we have proven earlier, and we are going to use this this formula on the following integrand. We have f of z over z minus z0, and we want to integrate over the the circle with center at z0 and with radius r. So let's now assume that f of z is less than mr. mr is some constant. Here we should have used the absolute value of z, otherwise this has no meaning. So, considering the absolute value of the integrand f of z over z minus z0 to the power of 2, we have that this must be less than this constant mr stated here over the absolute value of z minus z0. But z is some arbitrary point on the circle, so this difference must be equal to r. So this is equal to capital M over capital R to the square. So now, using this Cauchy integral formula, we have that the absolute value of the derivative of f at the point z0 equal to this. And now we are taking the absolute value, so this guy will just be 1 over 2 pi, and we have that the absolute value of this integral, using what we had on we stated here, namely that generally we have this inequality, are using this inequality for g of z equal to this integrand. So then we obtain the following. We obtain that this integral must be less than our upper bound for the absolute value of the integrand on this curve, which is this number, multiplied with the length, the curve length, which is 2 pi r. So now we are able to see that this is equal to 1 over r multiplied with mr. But now we have stated, if we state that the absolute value of f of z should be bounded, then this must be some value which is bounded for any value of r. So we then note that when r is going to infinity, this must go to 0. So this means that the absolute value of the derivative of the function f at z0 must be 0. And if this is true, then f of z must be a constant. It's not possible for a function which took an arbitrary point in in the complex plane z0, and we found that its derivative is equal to 0. Then of course the function f of z must be a constant throughout the complex plane. So this completes the proof.